So today we're going to talk about the Seifert-Van Kampen Theorem, sometimes just referred to as the Van Kampen Theorem, but that's kind of, tough for Seifert. So what this is a nice result in algebraic topology that'll help us calculate the fundamental group. And sometimes the way this is taught is you're given the statement of the theorem, a very complicated, hard to digest statement, and then you're given lots of examples, and hopefully by the end of the lecture you understood the statement that was at the beginning of the lecture. Today we're going to kind of flip that, where I'm going to begin with a very simple example, see if we can kind of get an intuitive grasp of what goes on, and we're going to build up the theorem along the way. We won't see the full proof of the theorem, it's quite technical. You can read about it in Hatcher, but hopefully I give you enough intuition along the way that by the time we see the first and ultimately the final version of the theorem, you have some intuitive grasp for it. But let's look at this space here, where this is just a wedge of two circles. So here I'm just looking at S1, wedge S1, and I want to think about what is the fundamental group of this space. You can think about the base point being here, but it's path connected, so wherever you pick your base point, that won't change the fundamental group. So you tell me, what is the fundamental group of this space? Maybe, give some coloring to him if that helps. You can think about this as being, there's some kind of path here, right? So here's like one thing in this fundamental group. I don't know, let's call this like A. So here's one thing in the fundamental group, A. And hopefully you at least believe that that A is distinct from this guy over here. There's no homotopy from this loop to that loop, right? Is that believable? So this A and this B are distinct. So there's at least two things in this fundamental group. A is not homotopic to B. What else is in this fundamental group? Oh, powers of A. So you could have like A squared, or A cubed, or in general A to the n, and those are all distinct. Just like when you have just a single copy of S1, all the powers of A are distinct from each other, right? And likewise, we have all these powers of B, and they're all distinct from each other. B is not homotopic to B squared, is not homotopic to B to the n if you have different powers. And just as A is not homotopic to B, it should be pretty obvious. I mean, we'll come back and we'll check this with the theorem in a minute, but hopefully you have a good intuition that like A cubed is not secretly B to the 17th, right? There's like, if you're going around this loop however many times, there's no way to homotope that to going around this loop any number of times. So A to any power is distinct. A to whatever power you want is not homotopic equivalent to B to any power, except for in the dumb case where it's 0 times each, right? Okay, so this is for m and n non-zero. Okay. If you're going around 0 times A, that's just constant. 0 times B, that's constant. So there's that one. Okay, so we have powers of A, powers of B. What else can you say about this guy? Yeah, let's think about AB. So AB is the loop where you go around A and then you go around B. AB is we go around A and then we go around B. So hopefully this is helping you get the idea. You go around A and then you go around B. Let's think about BA. BA would be the one where you go around B and then you go around A. First go around the B and then you go around the A. Are those homotopic to each other? I'm saying one person do this and one person do this. Well, what's the homotopy? It's like, I'm first going around A and then B. How can I change that to first going around B? And the problem is once you go around A, you're stuck going around A. So if you're going around A first, there's no way to change that to going around B first. Is that believable? Try to say, no, these are not homotopic. Going around A, you can't then go around B. Like, AB is not the same as BA. Because you've gone around A first, you've locked in going around A. And in general, it's like you can think the elements of this pi1 are things like any combination of A's and B's. You go around A 4 times, you go around B 2 times, you go around A -3 times, you go around B 1 time, and that's just the way it is. And there's no way to really change that, because once you go around A, however many times, you're stuck going around A that many times. You can't homotope it away. Just as we saw in S1, you can't homotope away going around A so many times. Now what you could do is, if I told you something like it's A squared, A cubed, B to the 4th, A, B to the -2, B, you could tell me what that's homotopic to. Because you would say, well, A squared and A cubed would just combine to be an A to the 5th. And the B to the 4th is fine, and A is just A. But B squared, -2, and B to the 1 here is just B to the -1. So it's like we can combine things within the A and the B. Going around A twice and then another time is the same as going around A 3 times, right? You're just changing your parameterization. But that's all we can do. So I mean, we'll verify this in a second, but hopefully intuitively this makes sense. So how do we write that? Well, 2 ways we could write this. One is we can say that this guy has presentation, group presentation, just A and B. So here, this is called a group presentation, where I'm just writing, it has generators. These are generators. These are my generators of the group. And this is my group presentation for the group. Another way to write that, what we've described here is a free product of 2 copies of Z. One that's generated by A and one that's generated by B. So this here is a free product. This is called the free product. And indeed, this group here is just called the free group with 2 generators. With 2 generators. It's free in the sense that A and B are free from each other. A does his thing, B does his thing, there's no interacting. A and B is not B and A. You can combine your A's when they're next to each other. You can combine your B's when they're next to each other. But besides that, A and B are independent. They don't interact. Okay. Hopefully this is believable. Because this example is meant to motivate my first version of Van Kampen's theorem. I won't even call it a theorem, I'll call it a proposition. Because we're going to build up to make it a little bit stronger. But here's my proposition. Here's the weak version, or special case of Van Kampen's theorem. If you have some topological space, X, that's equal to the union of 2 other spaces, A and B, where your A and B are open sets, and A intersect B is quite nice, the nicest thing possible. We call it simply connected. This is my special case when the intersection is simply connected. What do I mean by simply connected? We mean 2 things. Simply connected means 1, that it's path connected, and 2, that the fundamental group is trivial. The fundamental group of A intersect B is trivial. For example, if the intersection is contractible, if it just contracts to a single point, then this is what it means to be simply connected. So if X is 2 spaces that overlap, like in a single point or something contracts to a single point, then pi1 of X is isomorphic to the free product of pi1 of A and pi 1 of b. Okay. Let me go back and show you how we would apply this to this case, and then we'll look at some more examples to get some more intuition. So let's come back here. You might think your big A and big B should just be the circle A and the circle B. The problem is these are not open, right? So I want to make sure that A and B are open. So how do I do that? Well, I'll modify this slightly so that my space big A will be the loop A with the little extra tails on them where this is open. I'm trying to draw parentheses here to indicate it's open. So it's like up to but not including some point. Up to but not including some point. So it's a little open space. Likewise, my space B will be this entire circle with two little legs coming out that are open at the ends as well. So both A and B are these circles with little legs. But note, these circles with little legs, like my A here, is really like this, a little fish. And my B here is really this, a little fish as well. Well, these things just deformation retract onto a circle, onto S1. So there's a deformation retract. That's to say it's homotopy equivalent to the circle. There's a nice homotopy equivalence just down to the circle. And this is also a nice homotopy equivalence to the circle. So Van Kampen's theorem would then give me that pi 1, or at least the special case of Van Kampen's, of S1 wedge S1 is just isomorphic to, well, wait, let's check the intersection. What can you tell me about, blue and orange, what do you get when you mix those? Some kind of purplish color that I do not have. We'll say it's green. A intersect green. Yeah, this is kind of yellow, right? So yellow and blue gives you like greenish. This is good. What's the intersection of these guys look like? It's a little X with open ends, right? These are open endpoints. Maybe it would be easier if I drew like open circles here to indicate, open ends, right? Doesn't really matter if it's open or closed in this case. The A and B need to be open for this proposition, but here, who cares if it's open or closed? The point is when you have a little X like this deformation retracts, or this is contractible. This is homotopy equivalent to just a single point. This is a simply connected space. The pi 1 of this is trivial, right? Like all the paths you can think of in here are homotopy equivalent. You can just, slide them all to the origin, however you like. So this is homotopy equivalent to just a single point. So we can use this proposition, which means pi 1 of S1 wedge S1 is just pi 1 of A free product pi 1 of B. But since A and B are homotopy equivalent to just circles, S1s, this just ends up with the free product of Z with itself, just like we said before. So sure enough, what our intuition was telling us is exactly what this Van Kampen's is trying to say. Okay, are we happy with how this applies in this setting? Okay. A couple of things I could note. Let me note a couple of things. So we've just said that pi 1 of S1 wedge S1 is a free product on two copies of Z. Anyone want to guess what is pi 1 of S1 wedge S1 wedge S1? If I had 3 circles, Do what again? Yeah, I mean, like, the obvious guess is that this should be 3 copies of Z, the free product on 3 generators. How can you prove that? Well, we already know what it is on 2. I mean, like, how can we use this proposition to prove it? What should your A and your B be? Yeah, let A just be 2 of the circles. So let my space A be some space that looks like this, right? So A is a wedge of 2 circles with a little bit extra hanging over, like a little butterfly, maybe. And my space B is just the 1 circle with, well, I guess here you really need 4 guys sticking out, to make sure he's open. So, you know, you could have your B. It doesn't matter because these little hairs, little whiskers on the little mouse are just going to all contract down anyway. So your A is deformation retracts to just a wedge of 2 circles, to just S1 wedge S1, and your B deformation retracts to just a single copy of S1. So, and if you look at the intersection of these guys, okay, you know, the intersection just becomes, what is your A intersect B? Now green really is the intersection of blue and yellow. So the intersection of these is just going to be this little spider with 6 legs. I think Aristotle claimed spiders have 6 legs, right? I think that was a thing. Anyway, so it's a little 6-legged spider, but that deformation retracts to a single point. So this is simply connected, right? It's this pi 1 of this is trivial. It's just, you can imagine the homotopy just shrinking all the legs in. So you can see the homotopy equivalence here. Okay, so that means by Van Kampen's theorem, this should be isomorphic to pi 1 of A, free product pi 1 of B. But since A is just a wedge of 2 circles, this is the free product of pi 1 of S1 wedge S1 with a single circle, pi 1 of a single circle, which is now just going to be Z free product Z, free product, another Z, right? Okay. And like if you believe this, then perhaps you should believe, I can write it up here, what is pi 1 of the free product of like n copies of S1? Sorry, the wedge product of n copies of S1. What I mean by this, this is my way of trying to write S1 wedge S1 a total of n times. N copies, right? And what would that come out to be? Yeah, this is just going to be the free product n times of Z, which we call the free group on n generators. Each generator corresponding to 1 copy of S1. And you can just prove this by induction. I mean, this just follows immediately from this by induction, right? So this is, you know, assume it's true for n minus 1, and then you can break this up to n minus 1 copies plus another copy, and you get it for n in general. Okay. What if we have some other kinds of spaces? Let's think about like pi 1 of S1 wedge S2. So S2 wedge S1. Help me out. What should my A and my B be? Yeah, so one of the spaces, call it A, would be the entire sphere with these 2 little whiskers sticking out. And what is B? Maybe this is a little bit harder to think about.
No, circle with it's just like this little open disk carved out from the sphere.
First let's go over what Moises said. Moises, you were saying you could draw B just to kind of like miss a point there. But what's the problem with that? What would the intersection then be? The intersection would be this line on top and this line on bottom, which is not path connected. So we have to choose our A and a B, so it's path connected. So this one's not going to work. So we have to fill in the whole circle, but now it's no longer open, because you come up and you have this point here where it's not open here. So what do we have to do? Yeah, you have like a little, with an open boundary, you have like this little disk glued on. So B might look kind of weird. It has this like open disk-like structure. You know, this little, with then the circle glued on. Oh, it's a ring! You put a ring and you have like an open, I don't know, something like that. And then your A was the entire sphere with these little whiskers. But hopefully it's not hard to see, like, just as before, this deformation retracts. You just bring those whiskers on in. It's like reverse puberty or something. And you get a copy of S2, and the ring, the ring, you just bring this open set, just deforms down to a single point, in which case you just get a circle, right? Now you can't contract it any further. This doesn't go to a point. S2 is not homotopy to a point, and not home-to equivalent to a point, and S1 is not home-to equivalent to a point either. So that's where it stops. But now you see, by Van Kampen's theorem, this is just pi1 of A free product pi1 of B, but that's just pi1 of S1 free product pi1 of S2. And you can tell me, what is pi1 of S2? Do you remember? Trivial, right. So pi1 of S1 is just a copy of Z, and pi1 of S2 is trivial. So this is like, words that have A's and powers of A's and then ones. But the ones don't do anything. They're all just trivial, right? So this is just, pre-producting with 1 is not adding anything. That's just a copy of Z. So this is the same as just S1. The fundamental group as S1. Which you can kind of make sense of, because it's like, whatever loop you think of, if you start here, any loopiness you do over in the sphere, you can contract down to a point. And so really all the loops you can count of is how many times are you traveling around the circle. So this is the same fundamental group as just the circle. But now that we've done all these examples with wedge product, you tell me, what's a nice proposition? In general, what is the fundamental group of some space x1 wedge with some space x2? This is exactly the free product of pi1 of x1 with pi1 of the space x2. And it's like, why? Well, you just make your space A all of x1 plus whatever whiskers or other openness you need on the boundary to cover a little bit of x2. You make x2 all of B all of x2 plus some whiskers or whatever it is bleed over into x1, but then those deform into just x1 and x2, right? And more generally, you can do a similar inductive argument like we did before, that the pi1 of a wedge of some xi, where like I goes from 1 to n, say, if you have n of these guys, it's just going to be the free product from 1 to n of pi1 of xi. So wedging spaces is just taking the free product of the fundamental group. Okay. So hopefully, this second part just follows by induction. we happy with that? Okay. Before I go any further, let me point out a difference between S1 wedge S1, which we have here on top. This is the space S1 wedge S1, with the space S1 cross S1. This is the product of the spaces. What is the space S1 cross S1? It's a torus. So one S1 you can think of as a circle, and then it's cross S1, which means at each point of the circle, you put another copy of S1. You know, at each point there's a copy of S1, and you know all the infinitely many points along, which fills out to just give you a torus, right? So let me redraw it without all those. Well, we can leave that if you want. This is just a torus. So, do you remember what pi1 of the torus is? I think we mentioned it briefly in a previous lecture. I think we either talked about it for like 2 or 3 minutes. Z cross Z. So how is Z cross Z different than the free product between 2 copies of Z? Z cross Z, you can think in here, your points are typically think of them as ordered pairs, right? So like you have 2 kinds of circles here. One kind of circle is looping around this way. Yeah, this is going to get way too messy. One kind of circle is looping around this way. The other circle is looping around this way. So we might think these are my A and my B down here. This is like my A and my B. These are my generators A and B down here. But if we compare AB with BA, what is AB going to look like? Maybe I have to draw a couple toruses here. Let's think about what does AB look like? Well, let me give these guys some directions. We'll say A likes to travel this way, and B's preferred direction is this way. So AB would be you first loop around A, and then you travel around B. Right? I gave a little gap here, but this is all your base point. Just trying to let you see what's going on. Here's your AB. Okay, I should have drawn this in orange. Here is AB. What does BA look like? What does BA look like? BA is you first go around B, and then you go around A. And I suggest that these paths are homotopic to each other, right? Maybe the homotopy isn't obvious to you. So maybe like the way you see it, because you might think like, well, here, I started at this point. Whereas here, or I did A first. So here I started at this point. Whereas here I started at this point. I did my B first. So you might wonder, like, how do I go from doing B first, then A, to doing A first, then B? You guys have any thoughts on that? Like, how can you kind of see that these are homotopic? What's the homotopy that takes me from here to here? Yeah, you're just going to slide this circle along, right? So at some point, like, you know, if this is time 0, at some point, like time 0.2 or something, what you start doing is, you know, you start at this base point, and you just start moving some percentage of the way along t. And then you do your circle. And then you go around. Right? So, and you just keep sliding that circle around for your homotopy until you end up in this configuration where you're doing the loop is at the end. So you first go around, then you loop around. So here's what this homotopy looks like. I'm trying to show you the homotopy. You just slide that circle around at each point. So you say, 0.1, and we start moving out a little bit more first, and then it goes around and so forth. And that's a nice continuous transformation from this loop to that loop. So you can think this space down here is a space where AB equals BA. Both would just represent 1, 1 in Z cross Z, right? So they represent the same thing in Z cross Z. But the big difference between the torus S cross S1 and S1 wedge S1 is down here AB equals BA, whereas up here your AB is not equal to your BA. Good? Okay. So let's do some magic. If we just have a circle, we said the fundamental group of that is isomorphic to Z. What would be the fundamental group of the complement of the circle? Of, let's say, Euclidean three-dimensional space, R3, minus S1. So what do I mean by that? I just drill out S1. So my space is all of S3, all of R3, sorry, often work in S3. All of R3 minus S1. What would that look like? Is it a torus?
Most like a torus.
Oh, you're getting some good intuition there. Yeah, so you're trying to visualize what this like complement of S1 looks like, right? Okay, good. So let's do some work visualizing this. So here we have, instead of thinking of this as S1, think of this as R3 minus S1. So the space is everything except for that little circle there. Okay. Well, we know pi1 is preserved when we think of things up to homotopy equivalence. Right now I'm just going to do a deformation retract. So I'm going to slide points in. In particular, all the points that are far away can be pulled in up to some boundary of some sphere around the circle. So here's my circle. And what I can do is take all those points far away and slide them onto the surface of this ball. Like a big old Dyson sphere around that circle. Okay, so here we just did deformation retract R3 minus S1 onto a three-dimensional ball minus the circle. Does it help us get a better handle if you can kind of imagine this better? Like all those points far away, you move close. We don't change anything inside. We just move all the points outside. Inside, we left all the points the same.
Could you say D3 for the...
Yeah, we can call it D3. Sometimes I use B3, but D3 is also fine. A three-dimensional disk, that's fine. Okay. So now we have a ball that has a circle that's been carved out. Now we want to think about some way, how can we take all these points inside the circle and kind of push them towards the sphere? And like the points out here, you can push towards the boundary of the sphere, but you might be kind of worried there's like points in the middle and if you try and slide them out to the sphere, you create discontinuities, where we have to do this in a continuous way. So you can't just push everything onto the sphere. You could if this was just like a single hole, but because it's a circle, you get problems. Like the point at the center of the circle doesn't know where he should get slid to. So we can't just deform this into a single sphere. Instead, I want to suggest that this space is actually deformation retracts again. It's a homotopy equivalence, but stronger. It's a deformation retract. This is a special kind, remember, of homotopy equivalence. We can deformation retract this to a sphere with a diameter line through the middle. Do you see that? Like all these points inside just come down onto the line. All of these other points come down to the line, and these other points are coming out to the... So it takes some time to think about this. One way you might think about it is like if you start filling this circle with air, and it gets bigger and bigger, like more and more, you fill up the size of the hole, it starts filling up until the hole fills the whole inside circle, and there's just a small line through the center. Like fill up the balloon, and as the balloon pushes, it would push all the points out either towards the end or towards the very center line. Are we seeing the picture in our heads? Okay. It seems like this takes some thinking, but convince yourself that this is how this deformation retracts. What is this space? Can you tell me something this space is homotopy equivalent to? You claim it's equivalent to what? S2? Wedge S1. How do you see that? Oh, okay. Another way to see this is you can think as a quotient map, or you can take this line in the center and slowly start moving these endpoints over until the endpoints touch. In which case, you'll just get a copy of S1 in the inside. So it's deformation equivalent. It's homotopy equivalent to a copy of S2 wedge S1. Topology is cool. So now we have that the fundamental group of the complement of a circle is the fundamental group of S2 wedge S1, and you've already told me what that is. What is that? Yeah, that's just Z. So you should think about like what this Z is. Like Z is a group that's just generated by one guy A. And here you're like, well, my A is just looping around the circle once, which is like going through the center once and then coming around. So my A here, you can think of as just like looping around this guy once. Because it's like, the only time you introduce fundamental group is when you loop around here. When you're moving around doing whatever else outside, you're fine. It's just keeping track of how many times you've looped around the circle. So now if you have initial loop, like let me give you some curve. I want you to really get a sense of how you work with these things. Here's a curve. What is he doing coming all over my math? Nasty curve, stop that. He's coming maybe nodding around, What is that homotopic to? Well, you just count how many times he loops around the circle. Here he loops around once. We keep going. Here he loops around once, but the opposite direction. So here he's looping around +1 times. Here he's looping around -1 times. And here he's looping around, again, the opposite. He's going the opposite of that A. So he's looping around -1 times again, which means this whole curve would be homotopic to the curve that just goes around -1 times. So hopefully this is beginning to give you a sense of like this fundamental group is a structure that represents what you have. And you can imagine pulling this tight. How you would pull this tight. We allow these guys to pass through themselves. That's fine. He can pass through himself, but he can't pass through the circle because the circle's a hole. It's drilled out. You can't pass through because there's nothing there in the space to pass through. And so you can kind of tighten this up. And then as you tighten up this whole green line, you end up with something like that. And then you have to see like, oh, well now this guy can just pull out and that +1 and -1 cancel. And you end up with just a single loop going once in the opposite direction. So I'm trying to show you visually what's going on with the algebra. Okay, that's pi1 of a complement of a single circle. Anybody want to guess what is pi1 of the complement of two circles? There's two ways I could write this. I could use this notation like S1 disjoint union S1. These should be S1s for circles. This is my notation for disjoint union, but this is kind of confusing, so I think I'll just say pi1 minus x, where I'll denote here my space x is just two circles. There's x. Okay. Any guesses on what this should be? Free product of z and z? Well, let's see it. What can we deformation retract the complement of x to? So if this is x, I want to think about the complement of x. How can we deformation retract? Well, we could take all the stuff on the outside again and bring it down to a single big old sphere around these circles. So that would deformation retract it onto a three-dimensional ball minus S. But there's actually something better that we could do. So, R3 minus, so we have just two circles. This was R3 minus X. And I had a deformation retract down onto here.
Pinch the middle.
Good! You can start bringing these in. And so now you can think about it as actually these two balls, the wedge product of these two balls, each containing a circle. And then what do we do to the inside of the ball? Well, we say, just like before, that's homotopy equivalent to just this ball and this ball with some diameter line through the center. It's actually deformation retracts onto that. But then there's a homotopy where you just start moving this diameter slowly until it is a S1 and it is a S1. And so what you end up with is that this is equivalent to pi1 of S2 wedge S1 with another S2 wedge S1, which is going to come out to be just a free product of S2 with S1 with S2 with S1. But all those S2s die, the trivial, so you end up with just a free product of the fundamental group of S2 of S1 with S1, which is just Z free product with Z. Where the generators here just represent like these two loops. One loop that goes around that one circle one time, and one loop that goes around that other circle one time. And so if you have some complicated loop, you just have to count how many times there's a loop around each of the circles, and you know what word it corresponds to. Keeping track of, first it loops around this guy once, and then it loops around him once, and then back here 2 times. That's like A, B, A squared, right? Okay. Are we happy with this? You want something more interesting. Okay, I'll give you something more interesting.
You don't know it.
Oh no, you want it. I can tell. Hopefully we're seeing though, that just understanding the wedge of two spaces helps you understand quite a bit. Quite a bit of things, deformation track down to the wedge of two spaces. What if I have a circle and a second circle. But I have them link once. This is my space Y. Sometimes this is called the Hopf link. This is two little circles that link once. Just whoop. Okay. What is pi 1 of this? Or, better yet, what is pi 1 of the complement of this? That's what we care about. What is pi 1 of R3 minus Y, where Y is just the linking of two circles. So we care about the complement of linking of two circles. What can we deformation retract that onto? Well, let's just pull in R3, all those points far away, to again some big ball. So at least we'll get this within some ball. And now I want to try to begin understanding what's going on in that ball. Like, how can I describe the inside of that ball?
Toruses going into each other.
Yeah, you kind of think like, if I start blowing up these holes bigger and bigger, like I start moving points away from them, these are like growing tori. And what does that end up looking like on the inside?
It's hard to measure.
Maybe. I claim that you'll end with just a single torus inside of that ball, which is now a sphere. So you start thinking about it, and you can think like points close to this circle get pushed to the boundary of this torus. You know, like they start getting pushed to the boundary of this little torus right here as you're pushing them out. So like, you know, you agree with that. All the points close to, around this loop can be pushed onto that torus, right? But now, just like before, how all these other points around the circle could be pushed to a circle. All these other points could be pushed onto that circle. Remember, like come back right here. You know, we had that all of these other points around that circle could be pushed onto a single circle. All the other points around the circle can be pushed onto the surface of the torus as well. So that's why you end up with that torus. So what you end up with is S2 wedge a torus, S1 cross S1. So the space is isomorphic to pi 1 of a sphere wedge a torus, S1 cross S1, which by Van Kampen, since this is a wedge product, this is just pi 1 of S2 free product with pi 1 of S1 cross S1. But this is trivial, so he dies off. So you have just pi 1 of S1 cross S1, which is a copy of Z cross Z. And as we've already talked about, Z cross Z is not the same thing as Z free product Z. Z cross Z is the A and B commute. This is commutative. The word for commutative is abelian. This is an abelian group. The A and B commute. Here the A and B do not commute. This is non-abelian. Abelian is named after a Norwegian mathematician Abel. And so he studied group theory, and so we name commuting after him. But these are different groups. So since they're different groups, this pi1 is not isomorphic to this pi1. Which means this space is not homeomorphic to this space. If the spaces are homeomorphic, they would have the same fundamental groups. Or this space is not even homotopy equivalent to this space. So this was the whole like magicians are liars thing, right? When magicians have rings together, they're in this situation. And they're claiming there's some continuous deformation from having two circles looped to having them not looped, without the circles passing through each other, which is exactly what's going on here. There should be, but if there was a way to move continuously from this arrangement to this arrangement, they would have the same pi1. And they don't have the same pi1. So we know there's no way to go from this to this. So I had like a 1-minute YouTube video of this. It has like 1.5 million views. And they all say they don't understand. Although some insightful people say, actually, you've proven that magic is magic, because you're showing the magician goes from this to this, which is like we've shown shouldn't be possible because they have different pi1s. So it's either magicians are like lying or they're actually magic, right? So I don't know what the right conclusion is.
Is magic logically consistent?
Yeah, like, at least magic and math are not consistent. And then there's that great scene with like Doctor Strange and Spider-Man. And they're like fighting, and Spider-Man knows math, and so he's able to defeat Doctor Strange's magic. And so we'll end on that note. Okay. Let's move to some more examples. Here's what I want to move to. Let's come back to this torus example. We talked about that the fundamental group of S1 cross S1 is Z cross Z. But could we deduce that using Van Kampen's theorem? So let me draw the torus. Here's my torus, S1 cross S1. Or just a torus. What would happen if we try to use, and I've erased it now, but I had this nice form, the simplified form of Van Kampen's theorem, where our proposition was, if some space can be written as A union B, where my A and B are open, and A intersect B is simply connected, where recall simply connected means that it is both path connected and pi1 of A intersect B is trivial, a group with just one element. That's what it means to be simply connected. Then we had that pi1 of A union B, my X, is isomorphic to my pi1 of A free product pi1 of B. What happens if we try to apply this to the torus? What would be two good spaces A and B that you might try? You might try. Let's just make A half of it. So up to some open boundary. Okay, if you haven't taken real analysis yet, this whole discussion of open may have been a little bit confusing, but think of the analogy with open sets when you have just like an interval. Okay, so this whole, I'm trying to show this whole side on both sides is like my A. This is my A. Well, A is just a cylinder with open ends. A is just a cylinder with these open ends. And B is another cylinder, and you just have them overlap a little bit, because we want to have some nice overlap. Yeah, you might try this. So B is also a cylinder like this. I shouldn't be spending so much time drawing this, because this is wrong. What's wrong with making A and B, these two cylinders? Yeah, my A intersect B is not path connected. A intersect B is like two little cylinders. This is not path connected. I forgot to use green. This is not path connected. Like, we want it to be simply connected. It's not even path connected. So can you think of another way? What are your A and your B? Where the intersection is path connected. This might be a little bit hard.
Have one kind of like wrap it all the way around, and the other just be a strip going around the outside?
No, because the strip will intersect at the top and bottom of the strip, which will give you two different circles, right?
Yeah, but what I'm saying is well, I mean, what you could do is just have one set be the entire torus, and then another set.
Well, if you're doing the entire torus, it's not going to help you in the decomposition if this is just X again. But I like the spirit of what you're saying. What if we have one be almost the entire torus, except for a little region? So it's everything else. Everything else, all of this other stuff is in one. And the other is just this little disk here. Right? Now the intersection, A intersect B, is path connected. A intersect B looks like an annulus with open edges, but looks like an annulus, right? This is not simply connected. This guy deformation retracts onto just a copy of S1. And you know S1 does not have trivial fundamental group. So this little baby proposition won't hold up for us. But there was a more general form of Van Kampen's theorem that says, as long as you at least have the intersection be path connected, at least the intersection is at least path connected, even if it's not simply connected, even if the pi 1's not trivial, this still holds, except instead of just doing the free product, we're going to do something called the amalgamated product. I think there's a U somewhere in there, but I'll just throw a bunch of A's down and hope it works. Amalgamated, that's probably right. Amalgamated, amalgamation, is that a U? No, these are all A's? It's a ton of A's. The amalgamated product. Okay. What is the amalgamated product? The amalgamated product can be understood by thinking that your A intersect B can be included into A. You have a nice inclusion map. But you also have A intersect B includes into B. So you have two inclusion maps. Both of these inclusion maps induce maps on pi 1. There's a map from pi 1 of A intersect B into pi 1 of A, where you just take something A intersect B, you include it in A, and you see what does it represent in the fundamental group. And same thing J. This inclusion map induces a homomorphism from pi 1 of A intersect B into pi 1 of B. These are both induced homomorphisms. What the amalgamated product does is it's going to add some relations to our group where the relations are going to correspond to seeing what happens when you take something in A intersect B and you include it in A. You look at what the inclusion of something in A intersect B is when you include in A. You look at the inclusion when you include it in B, and you set them equal to each other. This is for C, something in A intersect B. You look at your generators of A intersect B, you include them in A, you include them in B, and you set them equal to each other. That setting them equal is like gluing the two pieces together. And so I'm going to unpack this now with this example. This might seem a little bit abstract, but let me unpack it now with this example. Okay. Here we have our A intersect B. Here we have one space. Here we have the other. My intersection, if I think about pi 1 of the intersection, that's just pi 1 of the circle, right? So this is just going to, you can think of as being generated by some guy C, where C is just the loop that goes around here once. Here's my C. What this is telling me is that pi 1 of the torus is just isomorphic to pi 1 of this first space A, whatever that is, free product pi 1 of the second space B, whatever that is, add in the relations that come from the intersection, where those relations are just asking what is C in this first fundamental group and what is C in the fundamental group of the other piece. Now, the way this stands, you can probably very quickly tell me what pi 1 of A is. It's trivial, right? It's just a disk. And when you include C into A, it's also trivial. This circle C included in A just shrinks down to a point. But you might have a harder time telling me what is pi 1 of the rest of this torus. You know, like of the torus minus this whole. What is pi 1 of the B? What is it? S1. Wedge S1? How did you get that? Oh, very good. You're right. Yeah, this is excellent. So I'll show you another way in a second we can think about this, but this is very good. Your B, if you take a bite out of a donut, and you still have all the rest of the donuts, right? Then the trick is to convince yourself, if you start expanding that hole bigger and bigger and bigger, you can keep doing that until you're down with just like a single circle here, and like a single circle you can think of as kind of like being on the inside. You know, as that circle gets bigger and bigger, it comes up until you have just that. So you end up with just a wedge of two copies of S1. And so, you know, if on one of these we call the generator A, and on the other one we call the generator B, okay, typically I try and make these go the same direction. So let me make him go this way. A and B. Now, you can tell me, so what we've done so far, running out of space. Okay. This is Van Kampen. This is Van Kampen. We'll just give the Dutch credit. Van Kampen was a Dutch mathematician, Seifert's a Greek mathematician. So what we see now is that this pi1 of A, the space A, is trivial. So pi1 of S1 cross S1 is isomorphic to pi1 of A, which is the disk, pi1 of a disk, free product pi1 of S1 wedge S1 with some relations added in from the intersection, from A intersect B. We'll come and talk about those in a second. But what this tells us is, well, this guy's trivial, so he's trivial, and he's just the free product of two copies of Z, so he's just going to be like an A and a B from the wedge of S1 and S1. What are my relations? Well, my relation here should be the relation, what does the inclusion of C give you under one map, and set that equal to the inclusion of C under the other map. That's what I mean by this. The first map, when you include it into A, when you include this C into A, you're thinking of C, the circle, as just being inside a disk. So what is this guy right here? Well, in the disk, he's trivial. So this side of the equation is just a 1. But the other side of the equation is saying, oh no, it now includes C onto B. Include C here on B. So here's my C. What is that equivalent to? Well, it's not quite A. Good. As you start stretching this out, that circle will get stretched out until the point that he looks something like coming around the bottom, going around A and B, and then going around A and B the opposite way. Right? So he ends up looking like A, B, A inverse, B inverse. Which means that pi1 of S1 cross S1 is the group where you have AB, and you have this property that AB, A inverse, B inverse is 1. Yeah? What's another way to write that property? You can multiply the right-hand side by B. So multiply both by B, this gets canceled, you have now a B over here. Then multiply an A, the same as saying AB equals BA. So this is the group generated by A and B, where your AB equals your BA. And that's what we said before, is exactly what Z cross Z is. It's just where your A and B can commute with each other. So these are isomorphic. Okay. This may have been a slightly confusing way to see this in this picture. So I'm going to show you one other way to see this in the torus. And once you see it in the torus, you'll then be able to start figuring out what is the fundamental group of all kinds of other spaces once I show you the strategy. So we got 4 minutes, we can do this. Instead of drawing the torus like this, I prefer to draw my torus like this, where I glue a copy of A to a copy of A, and I glue a copy of B, let's draw it the same way to begin with, to a copy of B, right? You take a sheet of paper, you glue the opposite sides, you get a cylinder, you glue the top to the bottom, you get a torus. My two spaces now will be just the disk, which maybe calling it big A is confusing. Let me call it big U. And everything else overlapping a little bit. This other space, which I'll call B. Van Kampen's theorem is telling me, oh, notice, don't want to call this B. Trying to avoid A and B. I'm calling it V. And then my U intersect V is this annulus, but that just deforms onto a copy of S1. So here, it's generated by this copy of my little c. Van Kampen's theorem says that pi1 of the torus will just be isomorphic to pi1 of the space U, free product, pi1 of the space V, but then come in and add the relation, so it's actually an amalgamated product from U intersect to V. Just like before, U is clearly trivial. It's just a disk. Pi1 of U is just the disk. So this is just pi1 of the disk. So that's just trivial. That's trivial. So that's going to contribute nothing to it. But now you can see what pi1 of V is. You can see from this picture, what does V deformation retract onto? Just start pushing everything in V up against these walls. Now, as you push V against these walls, you end up with just a single copy of this loop A with a single copy of the loop B. And this is the same copy of A, because it's glued to himself. So this is also just a single copy of the loop A. Glued to that copy, so it's just one copy there, A. And this is the same copy B. So I have a single copy of A, a single copy of B. So you can see that this is trivial, it contributes nothing. Pi1 of V is just a wedge of two circles, so it's your A and your B. Same story we just told, but now it's much easier to see this circle. When you include the circle on the disk, it's trivial, so one side of the relation is trivial. When you include the circle in the blue space, you can push the circle out to the walls, and what is the circle? We push against the walls, it just becomes A, B, A inverse, B inverse. A, B, A inverse, B inverse. Are we happy with that? Okay, so now, really very quickly, in the last minute, I want to get this in today. What is the fundamental group of a two-hole torus? I'll just call this a surface with genus 2. That's my notation for two-hole torus. Do you remember how we can draw a two-hole torus? It's not a square. What do we draw? It's an octagon. Where you have some A1, B1, and then going backwards A1, B1, and then A2, B2, and going backwards A2, B2. Yeah? Okay. So, again, just like before, you can decompose the space as the union of these two spaces, this dumb disk, and this space, that's everything else. The unisection, just like before, is an annulus generated by, whose pi1 is generated by some circle C. When I go and I calculate my fundamental group, it'll be the fundamental group of this first guy, which contributes nothing because he's a disk, with the fundamental group of the second guy, so you end up with a group. The second guy is just a wedge of the four circles, A1, B1, A2, B2. That's where the second guy is homotrope equivalent to. Deformation retracts to a wedge of those four circles, because these four circles are the same as those four circles. They're glued together. This is a circle because these points, remember we talked before, these points all get glued to the same point. So all these points get glued to the same point. This was several lectures ago. But you can keep track of how stuff gets glued. All those points to the same point. So there's actually a wedge of four circles. With the relation, when you include the circle onto the yellow region, its identity. When you include it onto the other region, what do you get? You just push it against the wall. So you just get the relation A1, B1, A1 inverse, B1 inverse, A2, B2, A2 inverse, B2 inverse is identity. That's the group for it. Nice? And now you can do it for any, for any SG. In general, SG would be A1, B1, A2, B2 through AG, BG with this long relationship up to, AG, BG, AG inverse, BG inverse. Now you know the group of any surface. What you can show is no two of these groups are the same. In particular, if you think about what would happen if you made this group abelian, this identity would disappear. So if you made this abelian, it would just be 4 copies. It's a free group with 4 generators. That's not what this group is, but if you made it abelian, it's the free group with 4 generators. Versus if you make this group abelian, it's a free group with 2 generators. Since they're different when you make them abelian, they must be different to begin with. And any 2 of these are different. And so a nice corollary we have is that the surface with M holes, with genus M, is never homotopy equivalent. It's not homotopy equivalent. To the surface with N holes if M is not equal to N. Because the pi 1s are different. We're going to describe the pi 1s now. So there's no way you can take a 2-hole torus and find a homeomorphism or even a homotopy equivalence onto a 1-hole torus. Or you can't take a 14-hole torus and find a homotopy equivalence to a 3-hole torus. And maybe that's like intuitively obvious, like there's no way to map this in a continuous way onto this. But now we've proven it, right? That's what the fundamental group gives us. Okay, we're out of time, so we'll stop there for today.